And why in the world is this coming up? Autoplay. What in the world is that? Well, something must have wiggled that. Yes. All right. Go from current slide. Okay. Now, excuse me. Before we get started on the math part today, let's just go over end of the term stuff. Number one, have you done the student course evaluations?
No.
No yet? Not yet? Please do those. Please don't forget to do those. I know at the end of the term, especially at the end of the spring term, last test done, and that, you're out of there and you forget, whoops, I never went back and did that. Okay. I'd never even think that myself, I just forget it. Etch a sketch, shake it, and it's gone. So please don't forget to do your student course evaluations. All right, then how are we going to wrap things up here? We are now in 12.4, and we're going to get as much done in this today. And remember now, they put out an email a couple weeks ago about final exam schedule, and they had it wrong, okay? And I printed it, but didn't really pay attention to it until maybe a week or so later when I was starting to do something. I said, wait a minute, this is wrong. They listed final exams starting Monday. And every other calendar, the academic calendar, the administrative calendar, all the calendars had final exams going from Tuesday through Monday of the following week. And so I had emailed back, never got a response, and finally talked to my boss Friday, asked him about it. He said, oh yeah, she saw that, but she thought since she already published it, she would say it's up to the instructor. You can either have class or final on that Monday. They don't let us do that, but they can do that. Okay. So anyway, we're having class on Monday to get as much covered as possible. And then I will give out to you then your last test, which will be mostly chapter 12, unless we get significantly into some other chapter. And right now I would say probably it's going to be mostly 12, but I'll let you know then. I have to make it out before class on Monday, and hard to predict what we'll cover and won't cover. Now, the other thing about Monday is I'll be giving you back every test you've turned in so far, so people who haven't turned in a test, too late to get them back to me then because I'll already have passed them out. So please get your test in no later than the beginning of class on Monday. But if you can get them to me today, tomorrow, Friday, or Monday before class, up until class time, I'll take them. Now, your research papers, I have to have them by Monday, okay? Otherwise, you start losing points after Monday. I have to have your test by Monday and after that, there is no makeup. I mean, it's going to be zeros then because I can't return them. I can't accept a test after I've already graded the others. I've turned the others back to you. Okay, that's what I've graded the others, but turn it back to you. So anyway, that's where we're setting. Okay. All right, let's move on from there then. We last time did example 3. We're in chapter 12, vector value functions. 12.4 is tangent vectors and normal vectors, and we had done example 3. This is the end of it right here. And I'm going to get my pen changed, and let's do example 4. Any questions before we get going on this? All right. Example 4. Find the principal unit normal vector for the helix r of t is equal to 2 cosine t I plus 2 sine t j plus tk. Okay, tk. Sorry. All right. Now, they're sort of cheating here, but I don't think it's a bad idea to not cheat and actually go through it. What would you do first? Sounds like a good capital idea. R prime of t is equal to what then?
-2 sine ti.
Got it?
Plus 2 cosine t k plus k.
Plus k. Got it. What do we do next?
Do the derivative of t over the magnitude?
Yes, we need the magnitude of this. And that would be?
The square root of 2 sine t squared.
So that one more time. 2, oh yes, okay. Of 2 sine t squared. Is that what you said? Now I'm assuming you put that in parentheses to square it, right? Yeah, right. Okay. Now, and since you were squaring it, you left off the minus sign, right? Yeah. Okay, got it. Plus?
Plus 2 cosine t squared.
Okay. One more.
And then plus k squared.
No. Don't ever do the vector. Yeah, 1 squared. The coefficient of k, 1.
Oh, right.
Yeah. Okay. Now, what's that?
Will it end up being factor out 2?
Well, 2 squared.
2 squared.
Okay, that would be factor out of 4. And what do you have left?
Yeah, 2.
Second?
Or the square root of 2, right?
Okay, not yet. Okay. When you factor it out, you left the sine squared t plus cosine squared t, and you counted that as 1?
Yes, sir.
Okay, right. Okay, I got you. But then you have a plus 1. That last one at the end. So it's the square root of 5. Yeah. Okay?
I had taken the 2 all the way out of the, it's not right.
You'd have to take it out all 3 terms, and it's not the 2 in this term. Okay. So I believe that's right, square root of 5. Now, what do you do with that?
Put that in the denominator.
Okay. Of your r prime. What does that give you?
That should be -2 sine t pi plus cosine 2 cosine t j plus k all over
Root 5, yeah. I put them under each one. It doesn't really matter. Perfectly fine either way. Okay, but what do you do with that? Oh, and what I was getting at, what does that give you to divide this by that? The unit tangent vector. Yeah, that's why we did all that, to get the unit tangent vector. And what do we do with it? Your first answer works again. Your first answer works again.
Oh, take a derivative.
Yeah, all right. We take it. Okay, yeah, okay. I'll let you catch up. All right. What does that give you? What's that? That's your unit tangent vector. You take a derivative of that, you get this. This time you do lose the k because the derivative of a constant is 0.
That's what I didn't take my derivative.
What's that?
I hadn't taken the derivative yet.
Oh, okay. Oh, you got lost before that.
Well, I was writing it down. Yeah.
Oh, okay.
That's our normal.
Yeah. What's the definition for your unit normal? Principal unit normal vector. That's what we're looking for. That's your derivative of your unit tangent vector, meaning it's perpendicular to it, divided by the magnitude of the derivative of the unit tangent vector. Now notice, I do this on purpose. This is a unit tangent vector. That's a unit vector. That's magnitude is 1. But this one, the derivative of it, is not necessarily, so I don't put the hat on it, I put the arrow over it, meaning that's probably not going to be a unit vector. Okay? And then the next thing we've got to do is take because the unit normal vector is that derivative over it. See, it's the same pattern we did here. Take a derivative and then divide by its magnitude. Take the derivative of that one and divide by its magnitude of this one. So we need to take the magnitude of this. The derivative of the unit tangent vector, knowing that that's probably not a unit vector. So this will be the square root of
2 over root 5 cosine t squared.
the whole thing squared, right?
cosine
right?
2 sine t squared.
The whole thing squared, right?
It's a 2 over root 5.
Okay. I probably couldn't understand all that, but what did you say? Oh, okay. Okay. Now, since there's no k term on it, this one you can do what you were trying to do before.
Factor out the 2 over root 5 and then just say plus 1.
Yeah, you don't have a plus 1 here, though. That's what I said. You don't have a k term anymore.
What is it? The cosine squared plus cosine squared 1?
Sine squared plus cosine squared is 1, so you have 2 over root 5 squared, okay, which would be 4/5, but then when you take the square root of that, you have 2 over root 5. So that's its magnitude. Okay? I believe I'm right on that. Yeah, 2 over root 5 is the magnitude. Okay, so you take your unit tangent vector and divide by this, which surprisingly, maybe, okay, that's that. So this will be the unit tangent vector, the derivative of the unit tangent vector, which is minus 2 over root 5. And I'm going to pull this out in this time. Cosine ti minus, no, I pulled out the minus, so that's the plus sine tj, I'm sorry. Okay, I pulled out the minus, get it out of there, and there, okay. Divided by 2 over root 5. Well, look at that, that's why I pulled it out. That's supposed to be a 5, it doesn't look like one. 2 over root 5, these go out. And that gives this unit normal vector to be simply minus cosine ti minus sine tj. Yeah. Okay. All right. Which, if you think about it, you know that's a unit vector. Cos cosine squared plus sine squared is 1. Okay? So that's got to be a unit vector. Okay? And that's your unit normal vector. Okay? Now, the only question is that the principal? Is it pointing in the right direction? Well, most of the time this will give it to you that it does point in the right direction. But if you think about this helix going up like this, you're pointing inward. You see this, especially if you leave off the k here, these are pointing outward here, and when you, the unit normal vector has to be pointing inward, and so yes, that does feel like that's exactly the right orientation. Okay, so minus cosine ti minus sine tj. And this vector is horizontal because it's always pointing toward the axis, the center axis. Now, it could have been pointing this way, but then it wouldn't have been, you know, there is no k component, so it's pointing horizontally. All along the helix does that. So it's not in both directions, but I was trying to give you something to refer to. All right, so that's horizontal points toward the z-axis shown in the figure, and I don't think they show that. No, because this is example 4. But you can see it in your text. Okay. So let's move on to, sorry, my nose is running. I don't know why. Tangent vectors and normal vectors. Haven't we already done this part? Yeah. This we had already done last time. I just had to go back to get example 4. Okay. Yeah, okay. And I think we had done this too, right? Yeah, we talked about it pointing to the inside. And we talked about the curves in space. Now, we're ready for this. This is where we pick up after example 4. The tangential and normal components of your acceleration. Okay? Now, you haven't had physics, right? Have you? You haven't either. All right. I won't give a physics example then. Okay. Let's just take it mathematically. Purely mathematically. In general, part of the acceleration, I almost have to give it, okay, and they call it the tangential component, acts in the line of motion, and part of it, the normal component, acts perpendicular to the line of motion. In order to determine these two components, you can use the normal vectors, unit tangent vector t of t and unit normal vector n of t, which serve in much the same way as do I and j, representing vectors in the plane. They're perpendicular to each other, but they always are oriented in that way. So, I'm going to have to give physics somewhat over this thing. I don't know, and you probably have been exposed to this enough to know. If you have a displacement, right, you were here, you moved to there. Okay, that's the displacement. The time rate of change of the displacement, that's your velocity. Okay, and these are both vector quantities, by the way. And the time rate of change of velocity is acceleration. Now you have two types of acceleration. Okay? If you're going in a straight line, you only have one kind. You're either speeding up or you're slowing down. Okay, one or the other, or you're going backwards and doing it faster, or going backwards and doing it more slowly. Okay, you only move in one direction. But remember I said time rate of change of velocity, which is a vector quantity, that's acceleration. Okay, so there's three ways you can accelerate. One is you're going in a straight line, change your speed. That's an acceleration. Well, we're used to that. But even if you're changing only the direction, that's a change of velocity. Okay? And if you're only changing direction, that's an acceleration toward the center of the curve. If the speed's constant, but you're changing direction, you're accelerating toward the center. It's called centripetal acceleration, center-seeking acceleration. Or you could be changing speed and changing direction, and then you have a tangential component and a normal component. That's what we're talking about here. Okay? And they are perpendicular to each other. All right? The following theorem states that the acceleration vector lies in the plane determined by t and n, the unit tangent vector and the unit normal vector. So the acceleration vector, if r of t is the position vector for a smooth curve c, and n of t exists, there is a unit normal vector. Now, when could there not be a unit normal vector? When your acceleration is only straight line. You've not got any curvature at all, so there's no curve to point towards. Okay, there's no center to point to. Then there is no. Okay, so as long as the position vector is there, smooth curve, and indeed it is a curve, not a straight line, so the n of t exists. Then the acceleration vector a of t lies in the plane determined by your tangent vector and your normal vector. So acceleration has to be in that plane and some combination of those two. Okay? The coefficients of t and n in the proof of theorem 12.4, was that 12.4? Yeah. Are called the tangential and normal components of the acceleration and are denoted by a sub t. Now, a is not a vector, okay? It's the component of the vector in the direction of the unit tangent vector, okay? But it's not a vector. It's the time rate of change of your speed. What's your speed doing? How, are you increasing, decreasing, staying the same? So that's the derivative of your velocity vector, the magnitude of velocity vector. Now the normal component of your acceleration, the one that's pulling it around the curve, that is your velocity, magnitude of velocity vector times the magnitude of the first derivative of the unit tangent vector. Okay? Remember, the unit normal vector is in the direction of the unit tangent vector, and it still has a velocity component here, but the other component is your first derivative of the unit tangent vector. So you could write your total acceleration is your a sub t in the direction of your tangent vector, that's the tangential component, and a sub n in the direction of the unit normal vector. So this gives you both accelerations, the speed increase and the direction change. That's what that tells you, direction change. All right? Because your first derivative of your unit tangent vector is how you're changing your direction. Okay. Now.
That's like saying if you're running this direction,
yeah.
but you're weaving like this.
Right.
It's always pointing towards your center line that you're going down, like that?
Yeah, in a sense, yes. Yeah, that is it. Because when you're doing that way, as long as you're not making a loop, okay, like that, yeah. Yeah, if you're just weaving, yeah, then the unit normal vector is always pointing toward the inside of the curve. You're right. Okay, hadn't thought about it that way. The following theorem lists some convenient formulas for a sub t and a sub n. Okay, a is the component of the acceleration vector in the direction of the unit tangent vector. A sub n is the component of the acceleration vector in the direction of the unit normal vector. Okay, so here are some expressions of that. If r of t is the position vector for a smooth curve C for which n of t exists, in other words, is a curve, not a straight line. Okay, then the tangential and normal components of the acceleration are as follows. Like we said before, the tangential component of your acceleration is simply the first derivative of your speed, which is the magnitude of the velocity vector. Okay? Now, if that's not something that you have, it also can be written as the total acceleration vector, which maybe is an easy thing to calculate, dot product with the unit tangent vector. And frankly, I don't see how you can ever have this without first getting that. So it seems like this would be the easier thing to do. There may be exceptions to that. Or another way to do that, because the unit tangent vector is the velocity vector divided by the magnitude of velocity vector. That is the unit tangent vector, because this is your r prime divided by magnitude of r prime. That dotted with your acceleration vector. And it doesn't matter which order you dot them, because they're commutative that way. Now that, you could convince me, was an easier thing. Well, yeah, an easier thing to do. And here's why. Because first thing you're going to do with this is take a derivative and it gives you this, right? And then it's real easy to take a derivative of that and that gives you that. Well, then dot product that's easy, divided by the magnitude. Whereas over here, you got the magnitude, you can do that, you got to do that anyway. But then you got to take the derivative of this, and that may be a difficult thing to take a derivative of, the magnitude. But the velocity itself is not difficult to take a derivative of, and then a dot product is really easy to do. Okay? Or the component of the acceleration vector in the normal direction, as I told before, was the magnitude of your velocity, which is the speed, times the magnitude of your first derivative of your unit tangent vector, which you know how much mess you have to go through to get that. So this may not be particularly easy. But if you know this, and that's usually pretty easy to get, it's just the second derivative of your displacement vector, okay? Dot product that with the unit normal vector. But you have to go through this to get to the unit normal vector. So unless they give it to you, That to me would be harder. But let's break that down, okay? Ooh. This isn't intuitively obvious here, but if you think about it, it really is, okay? Your velocity vector cross your acceleration vector, that's going to give you a vector perpendicular to both of those, and you know the normal vector has to be perpendicular to the velocity vector, okay? It has to be. So that is going to give you a vector guaranteed to be perpendicular, but then divide by this, and still not really obvious how that helps. But here's the one that's really easy, okay? We said this one's relatively easy to get, right? Most of the time, either this way or that way, okay? So you've already got that right there, okay? A sub t, okay? And it's easy to get this. Maybe not quite so easy to get its magnitude, but it's still not a bad thing to get its magnitude. So take the square root of this, but then don't even bother taking it. Well, you have to take the square root of it, but then you square the answer, which gives you this thing minus this thing squared, and take the square root of that. You got it. Because these two things are perpendicular to each other, and this is merely Pythagorean theorem. There's your hypotenuse, there's one leg, and there's the other leg. Okay? So yeah, a sub n squared plus a sub t squared has equal to the magnitude of a squared. So the square root of that. So now, note that the normal component of the acceleration vector is always greater than or equal to 0 because this is a personal square root. Okay? The other one doesn't need to be.
And is that why you see that all the time? You'll see the square root of something squared because they're trying to keep it from being negative?
Yeah, that sort of is a way of talking about a magnitude, basically. The magnitudes have to be positive, yeah. So yeah, it is that kind of a thing. Also in statistics, yay, okay, when you're talking about a standard deviation, okay, if you just did deviation, let's say you had a weird looking thing here and you're trying to get the best line fit of it, straight line fit of it. If you just take the differences here, if you got pretty close to the best line fit, if you just add those differences together, they're going to come out awfully close to 0. Well, that doesn't say how well that line matches the curve, but if you square them, add them up, and then take their square root, that's what a standard deviation is. That's always got to be positive, so the worse you are from the thing, then it's that. Whereas you could be really lousy, but if all those added up to 0, you think you're in great shape. You know, standard deviation, if you're really lousy, then you square those to get even lousier. Okay. So yeah, that is a good way to look at it. So, the normal component of the acceleration is also called the centripetal or single center-seeking component of the acceleration. Sort of a physics term there. All right, let's do example 5. Find the tangential and normal components of the acceleration for the position vector given by r of t is equal to 3ti minus tj plus t squared k. Where would you begin? Yeah, why not? R prime of t is equal to...
That's also a v.
That is also v. I was just going to say that, but I was going to wait a minute to say it, but perfect. That's your v of t. And this is equal to? 3i minus j plus 2tk. Perfect. Okay. We're looking for a sub t and a sub n. Now let's flash back to our thing here. A sub t, we just said probably the simplest thing to do is this last one. Given what we know, well, we'll see. We'll do it both ways. It's either going to be this one or that one, I think. Too much work to do that middle one, okay? So, you want to do the first one first or the second one first? I really don't care.
Go with the first.
First one, okay. First things first. So let's do magnitude of your velocity vector, which we also call the speed. What would that be?
Would be the square root of 3 squared plus 1 squared plus 2t squared.
Right, in parentheses squared. And that would give you
Square root of 9 plus 1 plus, that'd be 10 plus 4t.
squared.
Yeah.
Yeah, 4t squared. Got it. Okay. Now that's your magnitude of your velocity vector, or your speed. Now you got to take a derivative of it. That's the part that's sort of a pain in the neck. But let's rewrite that as, not as radical notation, but as exponential, and that would be
t plus 4t squared to the 1/2.
10 plus 4t squared to the 1/2 power. Okay? And let's take a derivative of that. D of your magnitude of your velocity vector squared, not squared, D. Duh. Okay. 1/2 10 plus 4t squared.
Squared to the 3s.
You're integrating it. It's supposed to be differentiating. Okay.
To the negative 1/2.
Yeah.
Negative 1/2 times 8t.
8t. Okay. And the 2 will go into 8 4 times. So this gives you 4t times, well, 4t over 10 plus 4t squared, square root of that. Goodness gracious. The square root of this. Okay. If you wanted to go back to that. Okay. So this is your A sub t. Your component of the acceleration vector in the direction of your unit tangent vector. In other words, tangential to the motion. Yeah, in the direction of the motion. All right. So we've got the A part. Now, let's just compare, because it's okay to do so. Up there we got D. Let's just go on and do A. A of t is equal to what? No. Yeah. You take a derivative of v of t, right?
Right.
Derivative of 3 is?
0.
Derivative of negative 1 is?
0. Okay.
And derivative of this is?
It'll be 2.
2k. There's your acceleration vector. Okay? Okay, 2k? 2k okay? Okay. Yeah, let's stop that. All right. go back a slide and say it's V dot A divided by the magnitude of V. Now, I already figured out what the magnitude of V was. That was this thing right here. Okay? Well, let's do the dot product between V dot A divided by magnitude of V. Okay? And V is 3. I prefer component notation. Is that okay? It's just easier to write. 3 comma negative 1 comma 2t. Right? Dotted with 0, 0, 2. That's your acceleration vector, right? And then divide that by the square root of 10 plus 4t squared. Okay? Well, you dot these two together, you get 0. You dot these two together, you get
0.
And you got the last two together, you get 4t. Right? Over the square root of 10 plus 4t squared. There you got it. Okay? Without having to take this sort of messy derivative here. Because the derivative of the velocity is generally going to be pretty easy. The derivative of a magnitude is going to have to, or most of the time, involve a square root, right? And those are just a little bit messier to do. Gives you the same answer. I feel like this is a little easier. Just between you, me, and the fence post. Right? You got to take that derivative of the magnitude of the velocity anyway, but you don't have to take a derivative of the magnitude of velocity. Okay? So yeah, you came up with exactly the same answer, and I think this was easier to do. Just personally. Okay? Now, so that's the tangential component of the acceleration. I'm just going to leave one of these up here. Which you want me to leave, the first one or the second one? Doesn't matter to me.
So you said the second one is usually the easier way to go?
Okay, what's that again?
You said the second way we do it is usually the easier way to go?
I find it usually is. Because you do a dot product rather than a derivative. Dot product is usually pretty easy. Okay. Now, if you leave that one up there, then I'll remove this one, and I'll remove the derivative part down here. But we did have to have that other part here, so I'm going to leave that part because that's where we got this from. So this is our A sub t, the tangential component of that. So the second part says find the normal components of the acceleration for that position vector. Okay? I keep turning back a page where I need to be turning back. Well, where is it? Oh, I've already turned back the page. Sorry. I was on the wrong page to begin with. Okay. It's at the top of this page, so we don't have to turn it back anywhere. I can flip back one slide. Okay. So here we've either got the magnitude of the velocity vector, which we have, the square root of 10 plus blah, blah. We got that. Times the magnitude of the unit tangent vector. Oh, time out. Okay. To get the unit tangent vector, we've got to first divide the velocity vector by the magnitude of velocity vector. That gives you your unit tangent vector. Then take a derivative of that, which will involve a quotient rule and stuff like that. And then take a magnitude of that. Let's not, okay? Stay away from that, okay? The other is A dot N. Well, A is easy. We've already gotten that. But the N, we have to do everything we said before, plus divide by the unit tangent vector by the magnitude of the unit tangent vector. So that one's sort of out. The next one is a cross product. Now that's not too bad, okay, most of the time. But the third one, hey, that's not too bad at all, okay? And let's see what the third one is. A sub n. Now if you already had calculated, and we have calculated V and A, okay, and that cross product is not going to be hard to do, and we've also you know, done the magnitude of V. Well, actually, every part of that's been done already, or almost. We just haven't taken the magnitude of V cross. We haven't done V cross A and then haven't done its magnitude. So that might be a little harder, but let's look at that third one. This is equal to the square root of the magnitude of the acceleration vector. We've already got the acceleration vector, we just haven't taken its magnitude, squared, minus a sub t, which we do have, squared. Okay? Now, it does involve a square root, but the rest of it's pretty easy. Okay? Here was our a sub t, right? A of t. 2k. Pretty easy to take that magnitude, isn't it? Right. What is it? 2. Okay. So this will be the square root of 4. I've just squared it. Minus. Now we have to do the square root of the a sub t. Well, there it is, right there. A sub t squared, I mean. The tangential component of the acceleration, okay? We've got to square it, so that's going to be 16 t squared divided by the square root of, the square of a square root is just the argument, 10 plus 4t squared. Right? Okay? Now, that's not too bad. There's some algebra involved, and if you really don't like algebra, that's too bad, but we got to deal with it. So let's put this over 10 plus 4t squared and multiply it by 10 plus 4t squared. Okay? And what does that give us? The square root of, that's going to be 40, excuse me, and I can hardly read my writing there, but that's plus 16 t squared. I swear that's what it is, but it sure doesn't look like it. Okay, 16 t squared. I'm having to convince myself that's really what it is. Minus 16 t squared. Oh, now that's nice, isn't it? Okay, over 10 plus 4t squared. Okay? Now, I so much wanted to get something to come out of the radical. It's not, but we can simplify this by 2 will go into this 20 times, 2 will go into this 5 times, 2 will go into this 2 times. So that's the square root of 20 over 5 plus 2t squared. I'll apologize. I know that I have a cataract in my left eye that has gotten worse, and it's so hard for me to read. And I'm going to have it taken care of in June, but that's more than a month away. So it's, if I'm missing something here, and quite often I think I do, part of it is because I can't see it well, okay? But anyway, I think that's what we've got. Let's see if they got this too. This is example which? 5.
And
they factored out 2, yeah. Well, they did worse than that. Seems like I've left something out here. I can see the 2 root 10. No, okay. I can see a 2 root 5 in the numerator. Okay. We have the same answers. Okay. You can factor out of this a fourth, so that would be 2 root 5 over the square root of 5 plus 2t squared. Now take what they have, 2, and I'm going to put it back under the square root of 10 over 10 plus 4t squared, right? That's what they have. I just wrote them back under the radical. I pulled the 2 out, but put the others back in. Then divide this by 2 is 5, divide that by 2 is 5, divide that by 2 is 2, and that's exactly what we've got here then. 2 root 5 over the square root of 5 plus 2t squared. So why they left it just a little messy, I'm not sure. Now, notice they didn't do it the way we did. They took the dot product of the v dot a. Okay, so they were doing, oops. No, I'm sorry, that's it. See, okay. They did the cross product of v cross a, which was the third possibility in that table up above. And they did that. It wasn't a hard thing to do, but they did it and came out minus 2i minus 6j. Okay, now I'm not going to do it for you, but that is, they did it correctly. Okay, the normal component of the acceleration would have been then the magnitude of that cross product, which is easy to do. The magnitude of that is 4 plus 36, which is root 40, square root of 40. Okay, divided by magnitude of v, which we already had. And so, yeah, they came out with it that way. Because that cross product was not a bad one, and I said at the time, it's not bad, but it just takes some effort to do. The way we did it, we didn't even have to. We just did. Now, we had some algebra to contend with, but it came out the same. Okay. So pay your money and take your choice. You've already paid your money, so take your choice. Which of those, for the normal component of the acceleration, you have 1, 2, 3, 4 forms you can choose from. For the tangential component of the acceleration, you have 3. Okay? So this is example 5. Now let's watch and see how they did it. Okay, we'll erase all this and begin by finding the velocity, speed, and acceleration. Okay? Velocity is easy, you just take the derivative. We did that. Then they did the magnitude of velocity, which gave us that, which is exactly what we got, square root of 10 plus 4t squared. That's at any time t. Okay? Then they did the acceleration, which just came out 2k. Exactly what we got. Okay? Now, the first one, like we said, was pretty easy. Just dot the velocity, dot the component of the acceleration. That gave us 4t over the magnitude of v, which we just did at square root of 10 plus 4t squared. Dot. There's your a sub t. Now, they went back and did v cross a. All right. Add, if you remember how to do that, you put ij to k at the top. You put the first one here, and that was your, from the previous slide, 3 minus 1, 2t. Those were the components. And your a was 0, 0, 2. Okay? Now, there's a couple ways to do this. Probably the easiest way, in case you are not that caught up on your determinants, find the row or column with the most zeros in it. We know it's the third row. Let's wipe out that row and also that column. And what we're going to use is use that 2 here, but you have to figure out what position that's in, a plus or a minus position. Plus, minus, plus, minus, plus. Plus, minus, plus, minus, plus. Any way you get there is going to give you a plus. So that's going to be 2 times the cross product here, the difference of the cross products. This will be a minus I minus 3j. Now, I'm going to tell you what I did there. Okay? It's positive, the downward diagonal. Well, that's a minus sign here, so it's minus I. So that's where that came from. And it's minus the upward diagonal. Well, it was a 3j, but it's minus that, so it's a minus 3j. So that gives you the actual V cross A. We really don't need that. We want the magnitude of that. And the magnitude of that would then be, the magnitude of this would be 2 times the square root of 1 plus 4. No, 1 plus 9. Oh, sorry. Okay. And that would be 2 root 10. Okay? They actually did. They multiplied through with the 2 and then squared that. But just take the 2 on the outside and they'll give you 2 root 10, which is exactly what they got. And here's Charles. Now we have all 3 C's here in a row. Charles, Catherine, and Clark. Okay? Our V's, our D's, and our B's and J's aren't here yet, but the 3 C's are here. Okay. Now, again, that's not hard, especially it wasn't hard because you had 2 zeros in this row, and it's easy to determine with that. And that's how we did it. Okay? And we took the magnitude of it next. So, we got that. Okay? And we divide that by the magnitude of velocity, which we already had, which was the square root of 10 plus 4t squared. And that's why they came out with that awkward looking form. Because that's how they got it. But you can divide out, if you put all the radicals together and then divide out common factors, that gives you 2 root 5. When you factor out a root 2 from that one, and a root 2 out of this one would be 5 plus, did I say, yeah, 5 plus 2t squared. Okay. You're dividing it out inside the radical, dividing out a common factor of 2. So that, they give us the same thing. So that is our normal component of the acceleration vector. This is easy. The way we did it was easy too. The algebra was a little tougher, but the rest of it was not bad. All right. Any questions on that? Again, let's see, watch how they finish the problem too. They got the same thing we did. They just multiplied the 2 through there. That's fine. You could do that. The normal component, and they use that third description of that, V cross A divided by magnitude of V cross A divided by V. All right. Now, again, I find what we did with dividing out another root 2 makes more sense. Whoa! That is the last example they show. And by the way, this example, example 5, is also located at larsoncalculus.com, and you can see an interactive version of this type of an example. So let's back off then. I think we're going to have to back more than that. There, we'll back to here. And we'll do example 6. Goodness gracious. I think I know what's happening now. I had been trying to figure out why I feel this way every day. It's because my eyes get so stinking tired. And I'm almost looking forward to having the cataract removed. I've had the right one removed, and it was not a problem at all. But what will be a problem, because when the right one was that's where they put the distance thing. So things up close were fine then for about 9 years. Now they've gotten blurry, so that's why I have to have the other one. But when they take this one out, I won't be able to see anything up close because the new lens they put in is not adjustable. You know, it's only going to be, so for that first day or so, but I'm having it done on a Thursday, so I can recover the whole weekend. So by the time I get back on Monday, we'll be fine. But it was a pain. Okay, so let's do example 6. Find the tangential and normal components of acceleration for the helix given by r of t is equal to, oh, looky here, b cosine ti plus b, thought they were going to give us different ones. I thought that would be a pain. But this is the same one, b sine tj plus ctk. All right. Fairly similar to 4, I believe it was, except 4 had, no, was that 4? No, yeah, example 4. The B's were 2's and the C was 1, okay? But very generic here. All right, what would you do first? All right, your r prime of t, which you pointed out before is also your v of t, okay, is equal to what?
Negative b cosine t.
Derivative, yeah.
Negative b sine.
Sine, got it. You had me writing it wrong. Shame on you, okay. Sine of ti, and I write a j. Goodness gracious. All right. All right.
And that's plus b cosine.
B cosine t j
Plus ck.
ck. ck. Right there it is. Okay. There's your r prime. What do you want to do next?
Take the magnitude.
Okay, let's do that here if we can. Magnitude of r prime of t.
The square root of b sine t in the parentheses squared plus b cosine t in the parentheses squared plus c squared.
Plus c squared, is that what you said? Yeah. My hearing is bad too. I can't see, I can't hear, I can't talk, okay. Can't dance, I can't do anything. Okay. All right, let's do that. And can we simplify that any?
I was looking at it right. Should it wind up being b squared plus c squared?
In parentheses, in the radical. B squared plus c squared. Got it. Very good. All right. Here's your r prime. The reason I put it over there is we'll use it from over there. Let's continue. What's the next thing we do?
So now we can
Your first answer works okay again.
take a derivative.
Yes. And your r double prime of t is the same as v prime of t, which is the same as a of t. Okay? So, and these are all vectors, by the way. All right. And your a of t would then be what?
Would be negative b cosine ti
Got it?
minus b sine tj.
And with no k, because derivative of c is 0. All right. Now, glancing back at the previous page, tangential component of your acceleration is your v cross a, v dot a, which are these two. Okay, so this is a sub t is equal to the dot product of these two. Can we do that right now? Okay, let's write it down. V of t dot a of t divided by, oh, my back's itching like crazy. Ugh. Okay, divided by the magnitude of v, which we just did, or the speed. Okay, now can't we do that dot product? That's why I wrote them on top of each other. It makes it pretty easy. What do you get there?
Negative 1, 1, and 1.
Whoa, how did you get that?
V up here, we have
A dot V, these two dotted with each other. Right? This gives us a positive b squared sine t cosine t, right? Minus b squared sine t cosine t. Whoa! Plus 0. Okay? And that's divided by the square root of b squared plus c squared. Whoa, here, Nellie, what's going on here? What's our tangential component of our acceleration? 0. B squared sine t minus b squared sine t cosine t minus b squared sine t cosine t is 0. So we have absolutely no acceleration in your tangential direction. And if you ask yourself why, you're moving in a circle. And the only way you move in a circle is if you have a constant speed and your only component is inward. Okay? So sure enough, that's what we got. Not constant velocity for sure, but constant speed. Okay? So the tangential component is 0. No matter what your b's are. Now notice there, the b's have to be the same for your I component and your j component. And c can be different on the k component. Who cares about that? That component disappears when you do the acceleration anyway. Those two, as long as those are the same. Now if they're not the same, if it was ABC rather than BBC, ABC is American Broadcasting Company and BBC is the British, no, it's completely different. Okay, then you have elliptical motion and you do have a tangential component. But as long as that's circular motion, your tangential component is 0 of the acceleration. 0. Okay, velocity isn't, but goodness gracious, acceleration is. Okay, may have come as a surprise, but it shouldn't be too much. And then your a sub n really becomes easy to do. What would that be?
square root.
The square root of?
Magnitude of a.
Is what? Magnitude of, okay, you can do that if you want to. Magnitude of a squared, right? Minus a sub t, which is 0, okay? And what does that give you?
b squared.
Okay. Oh, you're going on and doing it. Let's do that. It's the square root of b squared b squared. You got it, because it's sine squared plus cosine squared. So this is b, right? That's it, folks. Sorry. Wish I could make it harder. Okay? So your normal component is all of your acceleration, because the tangential component is 0. So your only component is that way. Okay? Now, let me see if I can say this right. In physics, I know, have you had physics yet?
Yes, sir.
Okay. If you remember circular motion, and this isn't quite circular motion, but it's awfully close. It's a circular helix, and by the time it's over with, basically your acceleration is just like for a circular motion, because there is no acceleration in the up and down in the z direction here. And if you recall that circular motion, it was v squared. Goodness gracious, my eyes. Your acceleration was v squared over, no. Why did I start this? I had it in my head earlier. V squared over r. That's it. V squared over r. Okay? So it's your velocity squared, which we just found to be this, divided by your magnitude of this, which would be v squared plus c squared. That's not quite right. Let's forget that. Oh, v squared. Okay, v squared would be v squared. Okay, that's what I was trying to say. That's v squared plus c squared, because you're squaring that, and divide it by the square root of that, which is, oh, you got the t in there too. Sorry about that. Forget it. That's too complicated to try to work that one out. I thought I could give you something simple, but it wasn't. All right, let's do example 7. How are we doing on time? Yeah, we got plenty. Let's get Daniel here. We finally got a letter other than C. We've got a D. So we're missing the V, the B, and the J. Okay. We're on page 851. This is chapter 12, vector value functions, 12.4, tangential and vectors and normal vectors, and we're on example 7. We just finished 6. Here we go to 7. All right. Projectile motion. The position vector for a projectile shown in the figure. Please look at your figure in your book. Those who don't have books, let me just basically show you what it's looking like here. I can't hold it up for too long because I'm too weak in the decrepit for this. Okay. All right. Here's your position vector. This is a curve formed by the position vector. R of t is equal to, and we'll write it down in a minute. That's your projectile motion right there. Okay. You saw it. It wasn't a very good picture, but anyway. Here is your R of t. (50 root 2t). You know, I'm going to write it 50 t root 2, just because I hate writing radicals in front of my variable I, plus 50 root 2. I did it the way they did, but I think it's clear enough. minus 16t squared j. Okay. All right. It says find the tangential and components, and find the tangential components of acceleration when t is equal to 0, 1, and 25 root 2 over 16, one of my favorite times of all time, okay? Those 3 times, okay? They're not asking for the normal component, just the tangential component, okay? Now, what would you do first? Take a derivative. R prime of t. And what would that be? 50 root 2 I. It's yes in Navy, okay. 50 root 2 minus 32 t j. Perfect. Okay? All right. It's asking for the tangential component of acceleration. Okay? What we determined before to be the easy form was going to be the v dot a. We've got our v right here. This is your v of t. Easy to get. Now your a of t is your first derivative of v of t, which is the second derivative of r of t. So take another derivative, and what do you get? Help me, somebody. Anybody? It's what?
That would be 0.
0 for I.
And then negative 32j.
Negative 32j. And if you think about it, of course, only 2 of you have had physics. That your acceleration due to gravity is going downhill everywhere along the motion. Okay? We knew that. This is in feet per second. They didn't tell us, but I can tell you it is. Or did they tell us? No, they didn't. But I'll tell you, we're in feet per second. Feet per second squared is the units of acceleration there. Okay. Now, what did we... Oh, one other thing we needed to do, and what was that? I jumped the gun. Magnitude of your velocity vector, which is the square root of
parentheses 50 times 2 squared.
Yeah. I'm going to be really lazy and going to square that, so I don't have to write it twice. So 50 squared is 2,500, and root 2 squared is 2, so that will be 5,000, I believe. Tell me if I'm wrong. Okay, plus, and we take that one and square it, and that's not nearly going to be as nice. Okay, sorry about that. But it'll be this one squared, which is another 5,000, minus, twice the product of those. That would be 100 root 2 times 32, so that would be 3,200 root 2 t. Okay, I said I wasn't going to do that, but I did it because it was easier. Plus 32 squared. I should know that one, but I don't.
handout.
Yeah, pull out the black box.
1,024.
I should have known that. 1,044?
Yeah, 24.
24. I thought that sounded bad. 1,044 t squared.
1,024.
Yeah, it's 24. I wrote it that way. I said it wrong. You can't read my writing, though. Okay. I think that's better. Okay. All that's under the square root, though I don't run out of room. All right, so this will be, let me rewrite this. The square root of 10,000 minus 3,200 root 2 t plus 1024 t squared. All right, that's your magnitude of your velocity vector at any time t. All right, now what your tangential component of your acceleration is going to be, your a sub t. I think they don't put the up t in it. Okay, a sub t is equal to, what is it? The dot product of these two, r times a. By the way, if you got your book, this is on the top of page 850. Again, my eyes are so bad. Okay, the I component's 0 when you dot them. You dot the two j's there, and you get 30 times 50, 32 times 50, 1600. I think that's right. 1600 root t minus 1600 root t plus 1024 t okay. It's that thing divided by this thing. 10,000 minus 3,200 t, root 2t. I hope I haven't lost a root 2 something. No, there's a root 2 up there too. Okay, good. Plus 1024 t squared. Okay. Now I know there's got to be a way to simplify some stuff here. I know 4 will go into that, I know 4 will go into that, I know 4 will go into that. Will 16 go into that? I'm pretty sure it will. 16 will go into that. Will 16 go into 10,000? I don't recall.
625.
How much?
625.
625. Okay. So if we take out a 16, that's pulling a 4 out from here, and that would be, you said 625?
Yeah.
Oh, but I forgot my root 2. Yuck. Forget that. Yuck. I forgot there's a root 2 in that one too. But it still may not be a bad idea to do it. Let's go back and do it. Okay. Square root, we pull out a 4. This is 625 minus 200 root 2 t plus, and 16 will go into 1024. Tell me that. I should be able to figure it in my head, but it's too late in the afternoon.
64.
64. I should have known that. 64 t squared. Okay? Now, in the numerator, this would have been a 64 up here, and this would have been a 100 root t, root 2, because I pulled a 4. Oh, sorry. Supposed to be pulling a 4 out of that, not a 16. Yuck. Let me go back and do that correctly. I lost my root. Okay, factoring a 4 out of this would be 400 root 2. And factoring a 4 out of that would be 256, I think, t. It still seems like there should be more. See, so I divided out with 4. Still messy, really messy. Okay, so that's what our tangential component of our thing. What it's asking us to do is, bless you, those specific times. T equals 0. I think I can almost do that one. Okay, when t is equal to 0, this is a minus 400 root 2 divided by 100. So that would be a minus 4 root 2. Okay. That doesn't seem right. They got minus 16 root 2, which still doesn't seem right. Okay? Because I would have sworn that would be positive by now. And they're getting a negative. Okay, so I've done something stupid. Oh, I know what I've done stupid. No, I haven't. That's right. Well, I've done something dumb somewhere there and off by a factor of 4. Okay? And I'm not about to go look for it now. Okay? Then when t is equal to 1, it gets even worse as far as calculations go, but it's still doable on a calculator. And then when you got t is equal to 25 root 2 over 16, and you put that in here, you're basically going to lose a lot of your root 2's and stuff, and you're going to wind up with a 0. Now, oh no, I'm sorry, I was doing the, in my head I was doing the velocity vector, the tangent vector, but we're looking for the tangential component of the acceleration vector. The acceleration vector has a negative component everywhere, okay? And the reason for that is slowing down because you fired it here and gravity is slowing it down the whole time. So your horizontal, your tangential component is slowing down until it reaches 0 right there. And then it's, the only component you have is the vertical component, which is your minus 32. So yeah, these are making sense. The greatest acceleration is near the beginning and then gets less and less till it goes to 0. Okay, I did a math error somewhere there, but I'm not going to go back and find it. That finally finished 12.4, okay? And 12.4 homework exercises here. Do any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13. They're all at Calc Chat. 9's at Calc View. Any of the odds 15 to 19. They're all at Calc Chat. 15's at Calc View. Either 21 or 23. They're both at Calc Chat. Any of the odds 25 to 29. They're all at Calc Chat. 27's at Calc View. Do either 31 or 33. They're both at Calc Chat. Any of the odds 35 to 39. They're all at Calc Chat. 35's at Calc View. You can explore doing 41. I don't know if they will have that answer at Calc Chat or not, but you can look it up and see. 43 should be at Calc Chat. 45 should be at Calc Chat. Any of the odds 47 to 51, they should all be at Calc Chat. 53 or 55 should be at Calc Chat. And any of the odds 57 through 59, or 59 should be at Calc Chat. 61 should be at Calc Chat. Either 63 and 63 should be at Calc Chat. So I'd say do one of the others of those. Orbital speed, that would be either 65 or 67 or both. 69 is a true-false. It should be at Calc Chat. 71 should be at Calc Chat. And 73 and 75 are proofs if you want to look at those, and they're at Calc Chat. Okay? Now, we don't have much time to go. So let's quickly, we've got what, 5 minutes?
Yes, sir.
Okay, 5 minutes. Let's quickly go to, now why does this keep popping up? I do not know. Oh, I should have kept it up, shouldn't I? Now I have to bring it up again. I guess it lost the load somewhere there. All right, let me find it again. 12:5. Last section in chapter 12. All right, now, forgot to say this earlier. I'm sorry Clark left. But this is probably all we're going to do in chapter 12 when I get done today. So this will be what your test will cover from chapter 12. Now I'm going to go through with you on Monday. That's our last day of class. I'm going to quickly go through partial differentiation, and then I'll quickly go through multiple integration. I'll try to split it up about half and half. We're only going to do the practical parts of it. I'm not going to do the theory part. Sorry about that. You'll have to read the book for that. And just to get where that is going to be, functions of several variables, that's your partial derivatives. And basically, we're going to skip probably 13.1 and 13. 13.1 and 13.2 go straight to 13.3. Okay? We may do 13.5 if we have time. And then I think that's all we're going to do there. Then the second half of the time we have, that'll be about an hour. And the second half will be another about an hour. We're going to jump to, goodness gracious, 13 was a long chapter. Chapter 14, which is multiple integration. And that is probably going to skip 14.1 and do double integrals in 14.2, triple integrals in 14.6. Okay? Maybe even 14.7, but I sort of doubt it. So that's what we'll do on Monday. I want to at least expose you to partial differentiation and multiple integration. So selected pieces in 13 and 14. So my guess is your test, the final test is going to be the first 4 sections of chapter 12 that we just finished, probably 2 questions each, and then 1 question on partial derivatives and 1 question on multiple integration, probably double integrals. Okay? So in the few minutes we have left, let's move on to arc length and curvature. And our objectives here: find the arc length of a space curve, use the arc length parameter to describe the plane curve or space curve, find the curvature of a curve at a point on a curve, and use a vector value function to find frictional force. We're not going to get there. But let's look at arc length. Okay? The formula for arc length of a plane curve has a natural extension to a smooth curve in space, and here's what it is. If you remember, I don't know if you do or not, what the arc length of a plane curve was when it was R of t is x to ti plus y of tj. with no k component on it. Okay? On some interval a to b, then you do the integral, and this is the symbol S is the arc length. Integral from a to b of the square root of x prime squared plus y prime squared dt. That was it. Okay? In space, when we have a z component, you just include the square root under the square root plus the square of z prime squared. Sorry about that. Got the hiccups. Which is basically your magnitude of your velocity vector, the magnitude of that, which is basically, if you think about that, that's the speed. You're integrating the speed, because that's what magnitude of velocity vector is, r prime. But these don't have to be velocities, so don't get that confused. So it's probably easiest just to leave it as r prime of t, magnitude of r prime of t. Okay? How are we doing on time? Through? Over?
Yeah. Just
Run out?
Just right.
Second?
Right on time.
Okay. So we're not going to have a chance to actually do one, but that is what that is. Now, that would be the one we do next. Wow, what a weird-looking function. Why is it such a weird-looking function? It's the only way you can get that you take the derivatives of all those, square them, put them in a square root, and then to get them to work out anything you can solve reasonably. So they are really weird-looking functions. But we're not going to have those. We didn't get far enough for them. But in time, you can do this. So, number on 12. So I know how to do the test now. I'll do 2 questions on 12.1, 2 on 12.2, 2 on 12.3, 2 on 12.4, 1 on 13, whatever the one on partial derivatives, I think it's 13.3, and 1 in double integrals, which will be 14, whatever it was. Okay. Or it may be a triple integral. It just depends on how far we get. Well, I won't know. I'll probably do a double integral. Okay.
So you'll mention the test Monday?
Yeah, I'll give you the test on Monday. And you'll have, are you graduating this term? Any of you graduating this term? No. Okay, well then you have until the following Monday to turn it in. But don't wait until the following Monday to turn it in if you can finish it sooner. Get it to me as soon as you can. Okay? Now, I also am returning all the tests. I can't return research papers, but they are due in Monday, last day that you can turn those in without losing points. And all your tests are due in Monday, and that's the very last day because I'm returning the rest of them, and I can't return them to you if they're still, I can't accept yours after that because I've already returned the correct answers out there. So get them all into me by Monday, first, beginning of class. Huh?
Well, you said Thursday.
I can't hear you.
Well, you said Thursday.
No. Monday is the last day of class. Okay? And that's when I have to have everything turned in. Your paper, if you turn it in after Monday, you'll lose points. But all your tests have to be in by now, I think you're talking about my Tuesday, Thursday class. That Thursday is tomorrow. Those have to be in by tomorrow. The Tuesday, Thursday test. The Monday, Wednesday class, which is this one, they all have to be in by Monday. Okay. Monday of next week, Thursday of this week, lands in tomorrow. Does that make sense? Okay. All right. You're only in this class, right?
Yes, sir.
Okay.
I gave you my paper earlier.
Yeah, right. And you're only in this class too, or you're in, no, you're in one more? No, you're only in this class.
Yeah, Jordan's in the other class. I'm only.
Yeah, Jordan's in both and you're in just one. Okay. All right, good deal.